So last we left off, we were talking about chemical equations or chemical reactions. Um, and we had balanced a couple of them, and we will balance a couple more to make sure that you guys have a complete understanding. So just a reminder, we have our reactants, which are located here on the left-hand side. And then on the right-hand side of the arrow, we have our products. Now, we use coefficients to sit there to let us know how much we have of the molecule that we're talking about. So in this case, we have two water molecules. And then that's going to yield two hydrogen gas and oxygen gas, one oxygen gas. So let's see if you guys recall anything about balancing chemical equations. Pull up a whiteboard. Okay, so we're going to start with a definition of a type of reaction. We call this a synthesis or a combination reaction. Now, a synthesis and combination reaction is going to be A plus B. A and B represents any chemical that we're talking about or compound that we're talking about. And then that's going to make, it's going to yield AB. Okay, so let me give you a real example, and then we'll balance that chemical equation. So let's say we had sulfurate plus fluorine gas. And that's going to yield SF6 solid. Okay, so we're going to balance this chemical equation. So what would be the very first step that we need to do? Feel free to chime in.
List each element.
Okay, so let's go ahead and list each element. So we have sulfur. Yeah, a little bit further. Sulfur. And we have fluorine. Okay. On our reactant side of our equation, which side is the reactant side again?
The left.
Okay. And then our product side is right. Okay. So on our reactant side of the equation, how many sulfur do we have?
8.
Okay. And then on our product side, how many sulfur do we have?
6.
Nope. We
Oh.
want to look at the number that's right next to the symbol for the element.
1. My bad.
That's right. That's right. Okay, that's right. 1. Oops. All right, wrong spot. There we go. And then fluorine on our reactant side.
2.
And then on our product side.
6.
Okay, so is that balanced? Are they the same on both sides?
No.
No. Okay, so what can we do to start balancing it out? So what is the coefficient that we're going to use? So we have 8 on our reactant side of sulfur, and we have 1. So what can I multiply? This is called sulfur fluoride or sulfur hexafluoride. 8. So we're going to multiply by 8. So we're going to put a coefficient of 8 in front of the chemical formula. Okay. So now that basically means 8 times 1, which we know is 8. And then now we have how many fluorines on our product side? That's right, 48. Yep. So we multiply the coefficient by the number, which is our subscript. So then that would be 48. Okay, so now we know that we have 48 fluorine on our product side, and we have 2 on our reactant side. So what do I need to multiply the 2 by so that I would end up with 48?
$24.
Okay, so 24. Okay, so 24 times 2 is 48. And now we have a balanced chemical equation. Okay, so again, this type of reaction is called a synthesis or a combination reaction. Okay, how are you feeling?
This one I understand. I was doing the homework and I wasn't really too sure about the chemical equations that you have to balance where they have like parentheses. I think it's something like ionic. I don't know what it what exactly it was.
Okay, so can you repeat that one more time, please?
Yeah, I said with these I felt pretty good, but the ones I was having trouble with, like doing the homework was the one with the parentheses. I think it's like it's called ionic
The
or
ionic, yeah,
sorry.
polyatomic ions. Yes, yeah. We'll go over those too. So
Okay, thank you.
no worries. Okay. So since you're ahead of the game there, we'll go straight to the challenging ones. I was going to build up to it, but you know. Okay. So these reactions, the next ones that we're going to be talking about is called double replacements. Or sometimes they'll say displacement. Okay. So the generic form for this reaction it's going to look like this. AB plus CD is going to yield AD plus CB. So in other words, you're just going to replace your partner. So let me give you an example. So let's say we have potassium phosphate in an aqueous solution plus say nickel nickel 4 actually we'll do nickel 2 chlorate. This over. Okay. So a question like this, Juanita.
Yes. Uh-huh.
Okay. Okay, so there's two ways that we can approach this, right? One way is to do it like we've done in the past and where we separate things out. The other way is since things are going to be moving in pairs, we can also set them up in pairs. So let me give you an example of what I mean by that. Okay. So for instance, we have ClO3 over here. Oh, I screwed up. and we have ClO3 right here. So in other words, remember where I said AB plus CD is going to make AD plus CB. So this here is going to represent our D, and the potassium, the K, is going to represent the A. Okay, so it's going to be moving in pairs or in groups. So what I can do is I can actually write down ClO3 down here. And we're making it as if it's a single unit, like we're saying it's D, okay? So we're just going to keep track of how many of those that we have, okay? So for instance, it's in parentheses, and we look at what's on the outside of the parentheses to tell us the quantity that we have of the ClO3. So how many ClO3 do we have on our reactant side?
Sorry?
How many ClO3s do we have on our reactant side? So I'll say it again.
Is it 2?
It's 2. That is correct. So again, all we need to do is look at the parentheses, and we look at the number on the outside of the parentheses. That tells us the quantity of what we have on the inside. So since the ClO3 is on the inside, we have 2 of those. Okay?
That's it.
On the product side, how many of ClO3 do we have?
Is that one 3?
Nope, it wouldn't be 3.
Parentheses.
There's no parentheses, so then that means
so
one.
it would be 1. That's right. Yeah. Since there's no parentheses, we would only have 1. That's right. Okay, you guys see how that works?
Yes.
Okay. Now let's look at PO4. Okay, on our reactant side, how many PO4s do we have?
1.
On our product side, how many PO4s do we have?
2.
That's right. Okay. Now potassium, which is K. How many potassiums do we have on our reactant side?
3.
On our product side?
1.
Okay. Now nickel, which is Ni. How many reactant on our reactant side? Is there a number next to it?
Is it 1?
It is 1. And then on our product side?
3.
That's right. Okay, so I have 2, 1, 1, 2, 3, 1, 1, 3. Okay, so is that balanced? Are the numbers the same? That's right, it's not balanced. The numbers are not the same on the both sides. Okay, so what can I do to balance out the chemical equation?
Multiply 1 and 2.
Multiply 1 and 2. So I multiply, so we can start off with the COs, right? ClO3. So what should be the coefficient that I put in front of the ClO3? Multiply by 2. Okay, so then that means now I have 2 potassiums and I have 2 ClO3s. Well, that's great for the ClO3s, but does that work for my potassiums? No, it doesn't, because my potassiums still are not balanced. Okay. So let's go to the next one then. So, oops, sorry. Put 2 here. There we go. For the phosphate, which is PO4, I have 1 and I have 2 on my product side. So what can I multiply by so that it will be 2 on both sides?
2.
2. So I'm going to put a coefficient of 2 in front. Okay, so then that changes my potassium on my reactant side to 6. It changes my phosphate to 2. Well, my phosphate looks good, but now I have 6. So what should I multiply instead of having a 2 here? What should I multiply this side by?
3.
I should multiply it by 3? Or should I multiply it by 6? So I remove the 2. Initially, we have 2, right? So, but if I remove that 2, what can I put? Because you can only have one number in front of there. What number should be in front of there? If I wanted to balance out, I have 6 over here, and now I'm back to 1.
Would it be 6?
6. So I'm going to multiply by a total of 6. So that means I have 6 of this. Now I also have 6 of my chlorate, the ClO3. So then what can I multiply my reactant side by so that it balances out my product side for my chlorates? Oops, and so this is also 6. So what number do I need to put in front of here? So right now, I have, for my chlorate, I have 2 chlorates. So what times 2 will equal 6?
3.
3. Okay, so then that gives me 6 over here on my reactant side, 6 on my product side. And that also gives me 3 nickels down here. So I have 6, 6, 2, 2, 6, 6, 3, 3. Okay, so this is a shorter way of doing it, but a lot of people like doing it the longer way, where you list everything down individually rather than doing it together. Both ways will give you the same answer. You just got to work through it. Okay.
Okay, thank you.
No problem. Okay, I'm going to do 3 more. As we do them, we're going to talk about another. We have single placement reaction. So a single replacement reaction, or it's also called the single displacement reaction, depending on how you're looking at it. So we're going to do let's see. Okay, so in this case, we have magnesium is going to be reacting with manganese 4 chloride to make magnesium chloride and manganese. Okay, so how would I balance this chemical equation?
I can't see the product side after the plus sign. I just see Mg plus MnCl4. Hey, I need the fourth.
Okay, let me
Also,
slide it
close
over.
to a 5.
There we go. Is that better?
Yes, thank you.
Okay, so the first step is to do what?
List the elements.
List our elements. Okay. So we have Mg, Mn, and Cl. Okay. So how many Mg's do we have on our reactant side?
1,
Okay. On our product side,
1,
okay. And Mn. That's right, Chantel, 1. And then on our product side,
1.
that's right, 1. Okay, so it's 1 on both sides. Now, what about Cl? We have 4 on our reactant side and our product side,
2.
2.
2. Okay. Okay, so is that balanced?
No.
No. What do I need to do to balance it?
Multiply by 2.
Okay, what am I going to multiply by 2?
Cl.
Which- My Cl. So I have to put it in front of the coefficient on my product side or my reactant side?
Product.
Product side. That's correct. So I'll put a 2 as my coefficient in front of my magnesium chloride. Okay, so then that means I'm also multiplying my magnesium by 2. And now my chloride has a total of 4. Okay, so is that balanced?
No.
No. So what do I need to do to make it balance?
Multiply the reactive side by 2 again for magnesium.
Okay, here we go. Okay, now is it balanced?
Yes.
Good, good. Okay, questions? No questions? Good. Okay. So let me add another page. So we've done double displacement, we've done single displacement, we've done a combination. Now we're going to do a decomposition. So a decomposition reaction is when we break stuff down. So let's say we're doing sodium perchlorate. breaking it down to okay, so in this case, the generic equation would be AB is going to yield A plus B. Okay. So if we're going to balance this chemical equation, what do I need to do?
List the elements.
List my elements. Okay. So on my reactant side, how many sodiums do I have? Sodium is Na.
1.
On my product side,
1.
the Cl, how many do I have on my reactant side?
1.
And on my product side,
1.
and the oxygens, how many do I have on my reactant side
4.
4.
and on my product side?
2.
Okay. So what do I need to do to balance it?
I think put a 2 on the oxygen on the product side.
Okay. Okay. So then that would give me a total of 4, and I believe it's balanced. Okay. Not too bad, right? Okay, so we've done synthesis combinations. We've done single replacement. Done a double replacement. We've done decomposition, and we have combustion. Or we also call oxidation. Okay. So that's just basically when you have oxygen being added to something to either break something else up or to add on to something. So let me give you an example. So this is called methanol liquid. And we're going to burn it with oxygen. And we're going to make carbon dioxide and water. Okay. So first step.
List the elements.
Okay. Is it, well, how many do you have on my reactant side? How many carbons?
One.
On my product side?
One.
Hydrogens do I have on my reactant side?
4.
And then on my reactant, I mean my product side?
2.
And number of oxygens I have on my reactant side?
3.
That's good. You picked up that we have 2 here and we have 1 here. Okay. And then on my product side?
Also 3.
Okay. Is it balanced?
No.
No.
Okay. So what do I need to do to balance it?
Add a 2 to the hydrogen on the product side.
Okay. So I put a 2 in front of the water. So then that gives me a total of 4 hydrogens and then a total of how many oxygens?
6.
Are you sure?
I think it's 5.
Are you sure? Let's see. Are you sure on our,
3.
so
2 is
I
5.
have 2 times 1,
My bad. It's 2.
2 times 1 plus the 2 here.
So 4.
4.
Should be 4. That's right.
I got it right.
I'm sorry, that was my son.
Tell him keep on. He'll be teaching you chemistry here soon. So. Okay. Okay, so now is it balanced?
No.
Now, what am I going to have to do to balance it out? This one is a little more challenging.
You're gonna have to multiply. You're gonna have to multiply the whole thing. I think it's by 3,
Okay.
and you put the 4 in front of the O. I think. Hold on.
Okay, so right now, let's look at it. Right now we have 1 here that we definitely have. So that's going to be definite 1 over here. I'm going to underline that one in green. Okay, so I want to get a total of 4 oxygens. Is that correct? Okay, so what can I multiply by 2 so that I would end up with 3 because I have 1 here already. So I have 4 minus 1. So that leaves 3 oxygens that I need to end up with. So what can I multiply this oxygen gas by so that I can end up with a total of 4?
1.5.
Okay, so if I go 1.5 here, so then that's 1 times 2, so then that'll give me a total of 2 oxygens. So do I want 1.5 or do I want 3 halves?
3 halves.
I want 3 halves. Okay, so if I multiply this by 2, then that gives me 3 plus my 1. So then that would give me my total of 4. But what is the problem with this?
I think so. You have to multiply everything by 2.
That's right. I need to multiply the whole equation by 2 because I can't have a half of a molecule or 3 halves of a molecule, right? It has to be the whole thing or nothing. Okay, so we multiply everything by 2. And then I'm going to write our final equation in blue down at the bottom. So 2 times the coefficient in front of here is what?
1.
1. Okay, so 2 times 1 would be just 2. So we have 2 CH 3 OH plus 2 times 3 halves,
6/2.
Is it 6?
6 over 2. So then that would be
It's 3.
6 divided by 2 would be what?
3.
3. Okay. Yes. And then that's going to yield 2 times, what is the coefficient in front of the CO2?
1.
Okay. So 2 times 1 would just be 2. It's 2 CO.
2 plus 4 H2O.
And then you said 4 H2O. Okay. And that's big gas here too. Okay, so let's go ahead and confirm. We're going to do confirmation at the top. So we have how many carbons on my, what's this out now? How many carbons on my reactant side?
2.
How many hydrogens on my reactant side?
4.
Are you sure? Hydrogens.
Oh.
So there's 4 here, and then you're multiplying it by a total of 2. So what is that?
8.
8. Okay. How many oxygens do I have on my reactant side?
3.
Is
Are
it
you-
2?
Okay, I have 2 plus 3 times 2,
6.
6. Okay, so I have 2 plus 6 is a
8.
total of 8. Okay, because we get 6 from here and we get 2 from here. Okay, now on my product side, how many carbons? We're looking at the equation down here.
2.
2. How many hydrogens?
4.
You sure?
8. 8.
8.
Okay, how many oxygens?
8.
8. Because we have 4 here and we have 4 here. 4 plus 4 is 8. Okay, questions? And that was a little challenging, right? Okay, so recap. What type of reaction is this?
Synthesis reaction?
That's right. Also called the combination. Okay, what about this one?
The composition reaction.
That's right. Okay, what about this?
Displacement reaction. You guys are so efficient, I'm not even getting a chance to writing everything down. Okay, what about this? I don't think I drew it out, but
Is that the single displacement reaction?
that's correct. And this is an example of what type of reaction? Write it out.
The oxidation reaction.
That's right. Okay. Questions? No
Is
questions?
the third one a double displacement reaction?
The third one, yeah,
Okay.
you're right.
My bad.
No, that's all right. It's my fault because I didn't correct you. So, there you go. Okay, questions? No questions?
No.
Okay. You guys are doing great. It's like you've been in chemistry class for now, a month already, right? Month and a half almost. Sharing this white screen. And start sharing my other screen. Okay, can you guys see the content?
Yes.
Okay. So the next thing that we're going to be talking about is energy. So in chemical reactions, also in physical reactions, we often will have to use energy. The definition of energy is the ability to do work or to transfer heat. In chemistry, the primary way that we recognize that energy is happening is by heat, right? So we often think about the transfer of heat as means of determining whether things are happening. So we're going to start defining our equations based upon heat, whether we're putting heat into the system or whether we're taking heat out of the system. So the term exothermic. Exo means what to you guys?
Out, like to put out.
That's right. Okay. So an exothermic reaction means that the energy is being released to the surroundings or it's being released. Okay. So that means it's always going to be on the product side when it's exothermic. Okay. So if you think about something that's burning, right? The energy is being released. That's how we feel the heat. So like a log burning. So that's an exothermic reaction because energy is being released by us burning that log. Does that make sense? Now, the opposite of exothermic is endothermic. That's putting heat into the system. Okay. And I'll show you an example of that here in a minute. Now, there are two major types of energy. One of them is called kinetic energy, and one of them is called potential energy. Kinetic energy, kinetic basically means movement. We've already talked about the kinetic molecular theory. Do you guys remember that? Are you guys there?
Yes.
Okay, you're thinking, right? That's what it is. I feel those wheels turning.
Wait, can you repeat the question? Sorry, I was.
I asked, I said, do you guys remember the kinetic molecular theory?
No, I don't remember.
Okay, so the kinetic molecular theory basically says that molecules are moving, essentially, right? So
Okay.
even when they're ice, they're vibrating, but it's a very small amount that they're moving. And then as we increase the temperature, they move more, right? And then as we increase the temperature more, they move even more, right? And so this is going to be very important for us to kind of understand what's going on. A lot of cases with chemistry or chemical changes and physical changes, right? Because both of them require energy. So for us to go from ice to a solid, from ice to water, then that requires energy. We have to put energy in to melt the ice, right? Okay, so kinetic energy is just going to be the energy due to motion, right? And so if you think about it, what we're doing is we're putting energy in to move those molecules so that they'll be mobile when we change from a liquid to a solid. Okay, now endothermic reactions, as I said, is when you put energy into the system, right? Or another way of looking at it is that you're taking energy away from the surroundings and putting it inside the reaction. Okay, so exothermic reactions, you're like if you fill it and it's an exothermic reaction, it gets warmer. Endothermic reactions, as you fill it, it gets colder because it's pulling energy in from the surroundings. Okay. So when we talk about potential energy is the energy that's due to the arrangement of charged particles in a system. That's how we define it in chemistry. But just to define it in general, potential energy is the energy that's going to be associated with a location, right? And so if you move that location and, let's say you're standing on the top of a mountain. As you stand on the top of the mountain, you can calculate the potential energy. As you jump off the top of the mountain, you can calculate the kinetic energy as you change from your potential energy to kinetic energy. Okay, so very similar is the case with chemistry. The only thing is that we're looking at it in terms of arrangement, not just location. Does that make sense? So in terms of the organization of a compound in that system, or charged particles in that system. Okay, so often we have to equate energy to mass because energy is going to be dependent on mass. So here's a question. I want you to think about it. Is energy directly proportional to mass or indirectly proportional to mass? Or inversely proportional to mass?
Indirectly.
Indirectly. So if we say indirectly or inversely, then that basically means that as mass goes up, energy would go down. Okay. Now I want you to think about this. If I took a ball, right? And let's say it was a bowling ball, and I throw it at you at, let's say, 5 miles per hour. Okay. And I take a tennis ball and I throw it at you at 5 miles per hour. Which one is going to have more energy behind it? The bowling ball or the tennis ball? Now they're going at you at the same speed. Which one is going to hurt more? The bowling ball, right? Because why do you guys think that's the case?
Because the mass is bigger.
Because it has a bigger mass. So then that also tells us something about the energy, right? Because it's going to hurt more because there's more energy behind it. So as the mass goes up, the energy is going to go up. So when we make reference to directly proportional, that basically means that they both go up at the same time. Inversely proportional means that they're going an opposite direction. One will go up, the other one's going down. Okay? And so when we talk about energy, we often will make it comparable. So Einstein was known for this. And so he basically had said energy is going to be equal to the speed of light times the mass of the particle, right? And so that's why we get E equals mc squared. Okay. Another way of looking at this, Einstein was also responsible for just thinking about in the case of the bowling ball, right? Sorry. E, or often they would say Ke, kinetic energy, is going to be equal to 1/2 the mass times the velocity. Okay, so where V here is going to be velocity. M is going to equal mass. C, as they said, is the speed of light. And of course, E is going to be equal to energy. Okay. Now, gravitational energy, or not gravitational energy, potential energy is going to be associated with arrangement, or it's also going to be associated with mass, PE, is going to be equal to mass times gravity times height. Spell force. And H is height. Okay. So, and it's also going to be associated with, as we said, arrangement of particles or charged particles. Okay, and we'll talk more about that a little bit later. Okay, questions? No questions. Good. Here's something about muscle memory. Ah, that's good. I'm glad it's muscle memory. Okay, so units. Be clear. Units of energy. So joule is the most commonly used unit. It's our SI unit for energy. And it's defined as the force of 1 Newton over the distance of 1 meter. Okay, so 1 joule is going to be 1 kilogram times meters squared second squared. Units that we typically use is calories. Now, when we talk about calories, there are 2 types of calories. There's calories that are going to be associated with the energy that is required to raise the temperature from 1 degrees, um, sorry, from, sorry, raise the temperature of 1 gram of water to 1 degree Celsius. You're just increasing the temperature by 1 degree Celsius. Okay, so that's the definition of a calorie. That's how we define the calorie in science, and that's how we define it in the US. Now, we also have what we call food calories. Now, the difference and how we distinguish between them in science is that the lowercase c calorie is the one that deals with raising the temperature. The uppercase c calorie is the one that deals with food, because we think food is important, so we make it uppercase. Okay? And so the difference between those two is 1 food calorie is equal to 1,000 small c calories. Okay? And I'll write that down. Okay? Okay. So, and 1 calorie is going to be approximately equal to 4.18 joules. Okay, so we can also just write the conversion factor is 4.18 joules per calorie. A kilojoule is going to be equal to 1,000 joules. And then you could say 1 kilojoule and 1 kilocalorie. So then 1 kilocalorie is going to be equal to 4.184 kilojoules. So we can sit there and do this. Now, this is something that you're going to see throughout chemistry, and I want you to kind of pay attention to it. The fact that we put the prefix kilo means 1,000, and kilo, right? So that's 1,000 over 1,000, which cancels each other out. So that's the same thing as saying a joule per calorie is the same thing as saying a kilojoule per kilocalorie. It's going to be the same value. And so this is going to work out whether we use 4.18 for centijoules per centicalories. That looks really crazy. Okay. Or we could say 4.18 for millijoules per millicalorie. So long as those prefixes are the same, the ratio is always going to be the same. Okay? And so again, you're going to be able to apply this to other systems as well. Be familiar with it. Or other units. Any questions so far? So where are we going to start? What's our given?
4.25
Kilojoules.
kilojoules. Wait, 42.5 kilojoules.
Okay, so we have 4.25 kilojoules. And we need to change to kilocalories. How would I go about doing that? So what is the conversion from kilojoules to kilocalories?
It'd be 4.184 kilojoules per 1 kilocalorie.
Okay, so for every 1 kilocalorie, so joules is where we're starting off. Kilojoules is where we're starting off. So we want to get rid of that. So I always like to think of it as trying to get rid of the old flame, right? They're no longer a priority, so we're going to always put them on the bottom. So we want to get rid of joules and we want to go to calories, kilocalories. So 4.18, 4.184 kilojoules is equal to 1 kilocalorie. Okay, we saw that last slide. Okay, and so then that would give us our kilocalories. Plug that into our calculator.
Is it 10.16? And it'd be kilocalories.
Okay. Now, here's the question. Would it be 10.16 or would it be 10.2? How many sig figs are we starting off with?
1.
Are you sure?
You know what?
3.
Wait, I rounded up. It's 10.157.
Okay.
So I just rounded up to 10.16.
So you were just giving me a number just to give it to me, huh? Is that what you're telling me?
Yeah, I was guessing.
Okay. 10.1, said 10.1 to 157.
157, yeah.
Okay. Or 158. Okay. So our number that we're starting off with is three significant figures, right? Because there are no zeros in there. So they're all non-zero numbers. So all of those numbers are going to be considered significant. This here is conversion, right? This is here serves as a conversion. So you're not going to take that into consideration for your sig figs. Okay. The only thing that you're going to take in consideration here is the number that we're starting off with, the 4.25. So we want an answer that would be three significant figures. So my answer should be, final answer, 10.2. Because we'll look at this, the number that will be following the three significant figures, 1, 1, 2, 3. Since this 0 is a captive 0, it's going to count as a significant figure. So then that's 1, 2, 3. So we take a look at the number, that's a 5. And then following that 5, there's numbers following. So that means that it would be greater than 5. So we would round the number up instead of leaving it alone. So then we'd end up with 10.2 kilocalories. Okay, so then how would I change my kilocalories to calories? What is that conversion? Lower C calories, not food calories.
Multiply 10 to the third power.
Okay, so I'm going to multiply it by 1,000, right? Okay, so I have 1 kcal. And we know that for every 1 kcal, that's going to be 1,000 calories. Or 10 to the third. So we're going to end up with two. Yep. Okay. And then if we want to figure out the number of joules that 42.5 kilojoules is going to be, how would I go about that? What is the conversion from kilojoules to joules?
A 1,000 joules for every kilojoule.
Okay, so 1 kilojoule on the bottom and 1,000 joules on top. So we end up with 42,500. Okay, now these all have three significant figures. Again, this 0 here is a captive 0 here. So that'll be 1, 2, 3 sig figs. These zeros here are placeholders to let us know the value of it, how big it is. Okay. And then here, same thing. You have 1, 2, 3 sig figs. These two aren't considered to be significant. They're just placeholders to let us know the value. Okay, evaporation. So when we talk about evaporation, evaporation is going to be occurring. It's basically when we have liquid going into the vapor phase. Now, at the same time that that's happening, we also have vapor coming back into the liquid phase. So you're going to have both of them occurring simultaneously within a closed system. So here, this is just an example. We have a bottle of water or a flask of water. So then the water molecules, they're going to get enough energy, enough kinetic energy that's going to allow them to overcome the intermolecular attraction. So each water molecule is attracted to the other by what we call dipole moments, and we'll talk more about that, or we'll call them intermolecular forces. They're going to be attracting to each other. So you're going to get enough kinetic energy to allow for one of those molecules to escape. At the same time that you're going to get one of them escaping, one of them is going to be re-entering from the gas phase. So it's going to actually come in and it's going to bombard and then go back into the liquid phase. And so you're going to get what we call a case of equilibrium, where, and this happens in a closed system where you have some of the molecules leaving and some of the molecules coming back. Now, for this to happen, for us to get into the vapor phase, it's going to take a quantitative amount of energy to actually move 1 mole, we've talked about the mole, of liquid into the vapor phase at a constant temperature and pressure. Okay. Now, another way of looking at it, we call this the heat of vaporization. So this force has to be overcome for things to boil or to go into the vapor phase. Okay. So the intermolecular forces, they're strong enough, and you have to put enough energy in to get over the hump. So to allow it to start boiling, to allow the liquid to start escaping. Okay. So we have a boiling point, which is the point, the temperature which vapor pressure becomes equal to the pressure above a liquid, excuse me. And then that's going to allow things to boil. And so you've reached that point where you're starting to get strong enough to escape those intermolecular forces. And so you're able to get those molecules escaping. So this here represents the heat of vaporization. So as we're going from boiling to our liquid phase, so the amount of energy that it's going to take. So in this case, we're putting energy into the system so that we can reach that point. Okay. And then condensation is that we're releasing enough temperature or releasing enough energy so that now we're able to go back down into the liquid phase. Okay. The other thing that I want to mention here is that the heat of vaporization and the heat of condensation are going to be the same in value, but one is going to be negative, right? So when it's exothermic, when something is exothermic, it's going to have a negative value associated with it. Okay. So when it's endothermic, it's going to have a positive value associated with it. Because you're putting energy into the system, positive. You're taking energy out of the system, it's negative. Okay. Now those values are going to be comparable to each other. They're going to be the same value, but the sign is going to be different. Okay. So we said a liquid is going to be boiling when it's at equilibrium between the vapor pressure and the atmospheric pressure. So that's when we actually get boiling occurring. Now, what's happening in the case of the molecules are building up enough kinetic energy to try to escape. And so down here, this bubble is going to is represented by these molecules. So those molecules are trying to escape. They're building enough energy. And so you're going to get them moving. And so they're going to form those bubbles. And then the rest of the liquid is going to be all connected together. So you're getting the gas formation or vapor formation within the liquid itself. And then again, that's a result of the movement of the molecules. So my two favorite words I've noticed are okay and so. So I noticed that I say those quite a bit. Can you guys hear me?
Yes.
Okay, I'm just making sure that I'm not talking with my mic off. That happens. So. Now, physically, that's what we see. That's what we understand. But we need to put this in terms of an equation so we can do calculations, right? So we can calculate how much energy is needed or how much energy is going to be released from a reaction. And the way that we do that is we use this equation. So we're going to make Q represents the energy that's going to be required. And then M is going to represent mass. We're making the heat, or I'm sorry, we call it Q. We'll call it heat, which is just energy. Q is going to have to be proportional to the mass. Okay. Now, the way that we do that is by putting our constant. So the enthalpy of vaporization, or the heat of vaporization, is going to represent that constant. That allows it to equal the mass. So then we can say Q is going to be equal to delta H vape times mass. So delta H vape, or heat of vaporization, is going to be equal to the energy, or heat, divided by the mass. Now, again, the heat of condensation is going to be the same as the heat of vaporization. Only thing that the sign is going to change. Now, here's some examples of the heat of fusion and the heat of vaporization. Fusion is the point of going from a liquid to a solid. The heat of vaporization is the point of going from a liquid to a gas. Now, these are the different substances that you can see where water's at. That's the one that we're going to be more commonly using initially. So the boiling point of water is 100 degrees. The melting point of water is 0 degrees Celsius. The heat of fusion is 33 joules per gram. And then the heat of vaporization is 2.26 kilojoules per gram. Okay, so these are some of the common heat of vaporizations. And there's in the appendix, there's also some more that are available for different elements. So we have a question. How much energy is needed to vaporize 188 grams of liquid if the heat of vaporization is 1.13 kilojoules per gram? Okay, so we're going to remember this equation. Q is going to be equal to the mass times delta H vape. And here you could basically use the delta H of condensation, the delta H of fusion, as long as you know the mass and you're in the right phase that you're talking. Okay, so we go ahead and plug this in. Q is going to be equal to 188 grams. And we're going to be multiplying it by 1.13 kilojoules per gram. And at the end of the day, we know that energy should be in joules or kilojoules or calories or kilocalories. So then make sure our units match up.
Is it 212.44?
That sounds correct. So 212.44. How many sig figs should I have? How many did we start off with?
3.
3. So how many should we end up with?
3.
3. So you're always going to end up with the one that you have the least amount. Both of these are 3. So, but the heat of vaporization is typically a constant. So you don't typically use that as your to determine your safe phase. You use what you're starting off. My answer should be 212 kilojoules. Okay, questions. So because we go to this 4 is not greater than 5, so then we just leave it at 212. If it was greater than 5, then we'd round up. If it's 5 exact, then we would leave it alone. Or if it's less than 5, we would leave it alone. Okay. Any questions so far? Okay. So when we talk about melting, so we're going to be using the heat of fusion. And so, sorry, I got those backwards earlier. So when we're going from a solid to a liquid, that is the heat of fusion. When we go from a liquid to a solid, that is the heat of solidification. Again, they're going to be the same value, only thing, the sign is going to be changing, which direction you go. Okay. The equation is going to be exactly the same. It's going to be Q delta H M. So the only thing is that now we're using the heat of fusion instead of using the heat of vaporization. How much energy is required to melt 25.0 grams of ice at 0 degrees Celsius? Okay, so where can I find the value for the heat of fusion for ice? Any ideas? How about that table that we looked at earlier? Doesn't that make sense? So let's go back to that table. Heat of fusion of water is 33 joules per gram. I mean, 333 joules per gram. So that's the value that we're going to be using. So what is the equation again? Q equals what?
Delta H fusion times mass.
Okay. Okay, so delta H fusion was 333. Joules per gram. And we have 25 grams. 25.0 grams. Okay. We end up with the value
8,325 joules.
Okay. How many sig figs should we have?
Four.
Are you sure? How many did we start off with? For
Is
the
it
mass. We should have 3. So then our Q is going to be equal to 8,300 and 320. Now, since this is exact, although there might be a typo, since this is exactly 5, so we're going to leave it alone. And then, so this is going to be a 2 instead of we're rounding up because it was an exactly 5. If it was greater than 5, let's say it was 0.7 or 0.1 or 0.007, then we'd round it up. And so that would be my answer. Okay. Oops, clear. So although I rounded it up, that would be incorrect for if we're doing sig figs. Okay, so the next thing that we're going to be talking about is specific heat. Now, with specific heat, the equation is going to be somewhat similar to what we saw with just heat or the enthalpy. Specific heat, we're going to be setting Q proportional to the mass times the temperature. And so when we do that, we need a constant, a proportionality constant. And we call this proportionality constant the specific heat. So this is the specific heat of pure substances. So we're making the assumption that whatever we're talking about is pure. And there's a constant for our specific heat. Okay. And so the unit is for specific heat is going to be grams of substance per degree Celsius. Okay. Or I'm sorry. It's going to be not grams. It's going to be per gram. Or it's going to be joules energy per gram Celsius. Sorry, it's getting late. My head is just not thinking clearly. So here are some examples. So in this case, we have joules. The units are in joules per gram degree Celsius. These are our pure substances. And these are the specific heats for these values. And so again, the one that we're going to be working a lot with is going to be water. I believe there's something that deals with iron. Okay, so you should be familiar with those. Okay, so the question is, how much energy is required to change the temperature of 25 grams of water from 10.0 degrees Celsius to 50.0 degrees Celsius. Now, when we talked 2 weeks ago, 3 weeks ago, I believe, about the change in temperature, delta T. So delta T is going to be equal to T final minus T initial. Okay, our equation here is going to be Q is going to be equal, or our heat is going to be equal to M C delta T. Okay, so I like to look at it. It looks like MCAT. Okay, so that's how I typically remember. Q is equal to MCAT. So in this case, our delta T is going to be 50 minus 10. 50 degrees C minus 10 degrees C. That's going to equal 40.0 degrees C. So then we plug this into our equation. We need to go get since we're talking about water, we want to make sure that we're in the right state. Go back to the table. And we're looking for water or liquid. So it's 4.8. And that's joules per grams Celsius. Okay, so that's 4.18, and that's joules, grams, degrees Celsius.
I got 4,180.
Okay. Four thousand 180. And that would be joules. Okay. Questions?
I have a question about the chart. Do we have the chart in the packet?
That chart is not in the packet. On the exam, we'll provide you with the values.
Oh,
And most questions will provide you with the values.
okay, thank you.
Maybe in the future, I'll add it to the packet. Okay,
Okay, thank you.
no problem. So you appreciate the packet, so I should continue dropping them off.
I do.
Okay.
I think they're helpful.
Good. And for those who don't know about the packets, if you're at Harnell, I hand those out to you. If you're near Kalinga, if you're near Lemoore, if you're near Fireball, I drop off 5 sets of packets for the lectures, and then also the periodic table, the chemical packet that you guys can use on your exam. I drop those off at those locations in the Mesa building and in the library. When I'm in those areas. If we need more, let me know. Because I don't want to waste paper. Okay. Questions? Any questions? No questions. Okay. Now, when we think about calculating the energy, we have to take in consideration the phase changes that are happening. So if we're talking about pure substances, we always have to take in consideration phase changes that are happening. So in all of these cases, we have to take in consideration that we're going through changes to get to where we're going to be going. And this kind of basically outlines it so we can get a better view. But let me give you a visual so you can kind of see what's happening visually rather than just, okay? So here, if we start in the solid phase, so if we start with ice, the first thing that we're going to have to do is we're going to have to increase the temperature of ice so that we can get to the point where we can change phases. So this is the solid plus liquid phase. For us to get over this hump, we have to get over the enthalpy, right? So we need the enthalpy here. So this here is going to be Q is going to be equal to M times the specific heat of ice times that temperature change. And so in this case, if we're talking about ice, we know that the transitional state or the melting point is 0 degrees. So we're going from whatever value that we started off with, so let's minus 10 to 0. Then we have to get over that ice to liquid transition or that solid to liquid transition. And to get over that hump, we need to have the heat that's associated with that. So that's going to be the mass. Q is going to be equal to the mass times delta H plus. And then if we're going from a liquid to a gas, we're going to be going from 0 degrees to 100 degrees Celsius, or to our temperature where we're starting to get vapor. So here, this is that hump to get over from that liquid gas phase to get just into the gas phase. Okay, and then that is just going to be, Q is going to be equal to delta H vape. And then in the last case, this is getting over into our vapor phase. And so we're just going to say Q is going to be equal to the mass times the specific heat of vapor times the change in temperature. Okay. Questions? Okay. Okay, so let's do a sample problem. So let's say we're working with ice. So we're starting at -10. Degrees Celsius, and we're going up to 120 degrees Celsius. And we have, write this question, how much energy let's make it 110 and make it a little. Okay, so if I have 100 grams, so how much energy does it take to go from -10 degrees Celsius to 110 degrees if we have 100 grams of ice starting? Okay. So what we're going to do, we're going to go to that table, write down a couple of things, and then we'll work through the problem. Okay. Go back to our tables. Oops, wrong way. Okay, so we're going to be working in 3 phases. So we need the specific heat. Put these on the side here. So I have C of ice. So I'm going to say CI. And so that's going to be our solid. And so that's going to be 2.06. That's joules, grams, Celsius. We have C liquid. And that's going to be 4.18 joules, grams, Celsius. And then we have C gas, and that's going to be 2.00 joules, grams, Celsius. And then we're going to need our heats of enthalpies. For water. So we need heat of fusion, which is delta H plus. It's joules, grams, and that's delta H vape. And that's going to be 2.26 kilojoules per gram. Okay. Okay, now that we have those values, we're going to start off with minus 10 degrees, and then we have freezing happening. So then our Q is going to be equal to, we're going to use this value here, and instead of just C, we're going to put sea ice. So we have Q is going to be equal to 100 grams times 2.6. I'm sorry, 2.06 times our change in temperature. So we're going from minus 10, and instead of going to 110, we have to break it up because we're only in the ice phase. And so we're going to be going from minus 10 to 0. So our T final is going to be 0, and then it's going to be minus 10. So it's going to be times 10. Okay, so then in this case, and that's degrees Celsius, and we're going to call this Q ice. Our QI is going to be equal to 100 times 10 times 2.06.
2060.
That's correct. That's going to be joules. Okay. So that's going to be our very first value. So then we have that phase, the transition phase. So in the transition phase, we're always going to be using the enthalpies. So in this case, we're going to be using Q is going to be equal to M times delta H fuss. So we're going to say 100. Q is going to be 100 times our delta H fuss is going to be 333. And that's joules grams. So then those grams are going to cancel out. And then our Q, and we'll call this fuss. And that's going to be equal to
33,300 joules.
okay. And then we're going from, now that we're in the liquid phase, it's going to be from 0 to 100 degrees Celsius. So then this is our initial, this is our final. So our delta T is just going to be 100. Degrees Celsius times, in this case, we're in the liquid phase. So we're going to use our specific heat for liquid, which is 3 times 4.8. 4.18, sorry. And that's joules, grams, Celsius. And we're multiplying it by 100 grams.
$41,800.
41,800. and that's joules. And then that's going to be our Q liquid. Okay. And then now we're getting that transition from liquid to a gas. So we're going to be using the delta H vape. So our mass is 100. And we're going to be multiplying it by 2.26 kilojoules. Now, all the other values are in joules, so you need to remember that this one is in kilojoules per gram. So we should probably change this to joules. So we know that for every 1 kilojoule, that's going to be 1,000 joules. Okay. So if I remember correctly, so that should be 226,000 joules. And that's going to be our Q vape. And then in this last case, we're going to be using a specific heat. And so we're going from the temperature of 100 to 110. Okay, so then that's just a difference of 10. So we have our delta T is going to be 10 degrees. Our C of gas is 2.00 joules degrees C grams. And then we're multiplying that by 100.
2,000 joules.
Okay. And then that's going to be our Q gas. Okay, so our Q total that's going to be equal to our Q ice plus our Q fuse plus our Q liquid plus our Q vape plus our Q gas. So we add them all together.
I got 271,860 joules.
271,860 joules. Okay. And we should end up with, since we started off with, we're going to use this guy. So let's do this. We'll say 4 sig figs. Try to stay consistent.
Would it be 271,900? Is that what it was? I didn't see it.
Let's see. 271. Yep, 900. Okay. Questions? No questions? Now, it's not difficult. It's just tedious. Lots of the little equations and adding them up together. And remembering that you have to pay attention to the phases and include the transitions. Okay, can I clear the board or do you guys need time? Okay. Okay, so when you go through this process, drawing a sketch always helps, or having a sketch available always helps to sit there and go through that process, because then you can break it down each of the steps that you need. And that's what this basically tells you. Just try to get they call it a total heat flow sketch. Okay, so here's our question. Calculate the total transfer when 19.9 grams of ice, initially at minus 12 degrees Celsius, is heated to steam at 115 degrees Celsius. Okay, so first step, you should always draw our little heat flow. Okay, so we're starting off at minus 12 degrees. And we're going to be going up to, let's see, solid, liquid, and then gas. We're going up to 115. Okay, so, and we're talking again about ice. Okay, so we have our beautiful graph here. So what equation are we going to use for the very first one? From A to B.
MCAT?
We're going to use MCAT. That's right. So from A to B, we're going to use Q equals MC. We're going to be in the ice phase, so it's going to be CI delta T. Okay. And then what are we going to use from B to C?
Delta H times mass.
Okay, so Q is going to be equal to delta H of fusion times mass. And then what about from C to D?
MCL delta T.
MCAT. Now we're using the L delta T. And then what about from D to E?
Delta H times mass.
So delta H vape times the mass. And from E to F,
MCAT.
okay? And that's going to be gas. Okay. So from A to B, we're going to be using the temperature. So where are we going to end up at since we're still in the ice phase? So what is the temperature of melting? Ice melts at what temperature?
Twelve.
Is it the change is going to be 12, right? Because ice melts at 0 degrees Celsius. So it's 0 minus 12. Okay, so that's going to be our delta T. We're going to call this 1, this one 2, and then this is 3. So delta T1. And that's going to equal 12. Okay, because a minus times a minus, I say, is a positive. Okay, and in the case of, so that's going to take care of this, the fusion, and then our delta T2, that's going to be going from what temperature to what temperature?
0 to 100.
It's going to be going from 0 to 100. So our final temperature is 100 minus 0 is just going to be 100 degrees. Okay. Minus 0 equals 100. And then our delta T3.
100 to 115. So 115 minus 100 equals 15 degrees Celsius.
Okay. Okay. Questions so far? Okay. Okay, so we're going to go ahead and plug in our values. So we know that for our Q equals to CI, so this is our CI value here. So we have 19 point, ooh, our mass is 19.6 grams. We're multiplying that by 2.06 joules per gram degree Celsius. We already shown that this is times 12. And then we're going to go ahead and convert it to, okay. So then we end up with that very first Q. Call it QAB for short. That's going to be equal to 0.48 kilojoules. Okay. Our Q fuse, or our Q B to C, is just our mass times our delta H fuse. And so these are the values. So 19.6 times 33 joules per grams. We're going to convert it to kilojoules. And so we end up with 6.53 kilojoules. Okay. So from C to D, we're going to be using our MCAT. So in this case, we're using the C of liquid. So we know that that's 4.18. So we have 19.6 times our 4.18. And then our temperature change, we had calculated to be 100 times 100. And we're going to convert that directly to kilojoules. So we end up with 8.16 kilojoules. I mean, 8.19, sorry, kilojoules. And then for our QD to E, we're going to be using mass times the heat of vaporization. And so we're using the 19.6 grams times the 2.26, which is the heat of vaporization. And we end up with 44.3 kilojoules. And then we have sorry, this should be a D. My bad. D to E. Okay. And then from E to F, and my numbers are all E to F. Then we're going to be using a MCAT. So 19.6 grams times 2.0 joules per grams degree Celsius multiplied by 15. And then we're going to convert that directly to kilojoules. And that's 0.59 kilojoules. Okay, so then we're going to add them all up. Okay, so this symbol here, I'm going to clear what I have written on the side. So this symbol here means sum. When you're in math, you probably ran into it. So we're taking the sum of all of the different regions added together. And these are our values. Okay, questions? No questions? How are you guys doing? How's your heads? Can you guys hang on for about another 5 more slides? 6 more? So no answer is a yes answer to me. So perfect. Okay, so I have a personal question. I'm going to get up all in your business. How many of you guys have significant others? Or a really close friend that you hang out with? You do? Okay. So which one of your significant others, which one of you or your significant other have cold feet?
What do you mean cold feet? Like our feet are cold or like cold feet, like scared?
Oh, your feet are cold, not that you're scared to get married or anything.
Maybe me.
You said maybe you? Okay. Okay. So when you're in bed, do you put your feet on your partner's back or on their body
Yes.
somewhere?
Uh-huh.
Uh-huh. Why do you do that?
To get warm, to warm up, create friction.
Do they get warm or do they get cold?
They get cold.
They get cold, right? Okay. So this process is called heat transfer. Real case, right? So I had an ex-girlfriend. She would love to put her feet on my back. And so her feet were so cold, always so cold. So her feet got warm, but my back got cooler as a direct result. So if we have 2 different temperatures, one high, one low, when they come in contact with each other, right? Your feet, their back, when they come in contact with each other, the heat is being transferred with the one that's high to the one that's low. And then they're going to keep doing that until they reach a point of equilibrium. So you're going to get a temperature that's going to be in between both. So your feet warm up, but your partner's back stays cold, gets cooled down. Okay. And so this process is called heat transfer, right? There's major studies that are. And anytime this happens, you're going to reach a state of equilibrium. Okay. So if I put a hot cube of metal into water, what's going to happen to that water?
Would the water warm up?
Water's going to warm up. That's right. So the water's going to warm up. The hot cube or the hot piece of metal, what's going to happen to that?
Would it cool down?
It's going to cool down. Okay. So that's the process of heat transfer. Okay. So whenever we put something hot and something cold, you're going to get a point of equilibrium. And we're going to be talking about equilibrium quite a bit. This here is thermal equilibrium. The other type of equilibrium that we'll be talking about is chemical. Okay. Okay. It's almost there. Conservation of energy. So there are the laws of conservation. So we have the laws of conservation of mass and energy. So that basically says that the total mass and energy in the universe is fixed and it doesn't change, period. Okay. Law of conservation of mass is total mass of a reactant in a chemical reaction, or I'm sorry, chemical change is equal to the total mass of the product. So in other words, what you put in, you have to get out. Okay. So what you put in terms of our total mass, we have to get out. And so the law of conservation of energy basically says that the quantity of energy within an isolated system doesn't change. So in other words, energy within that system is conserved and it is neither created or destroyed. It's just going to be altered. Okay. So when we work on thermal, this is a little bit out of order here, but when we work on thermochemical equations, we've already talked about the heat of vaporization, the heat of fusion, but we also have what we call the heat of a reaction or the enthalpy of a reaction. So enthalpy represents the heat content of a chemical system. And we often will use the delta H symbol, which you've seen already. The delta basically means change, and the R tells us whether it here the R stands for reaction. Earlier we used fusion or vaporization, so you'll see that quite a bit. Okay, so things to remember: if our delta H of the reaction is a negative value, that means the chemical reaction is an exothermic reaction. If our delta H is a positive value, then that means that it is an endothermic reaction. Okay, so these are different ways of writing the same chemical equation. So here, this is our delta H. Now, I should also say there's stuff missing here. Fix this up at some point. So this is based upon per mole. Okay. Or often we'll say just kilojoules / moles per mole. Okay. Now, this here, actually, so this is the equation. And so one way of writing it is delta H equals minus 22. So we can write it outside of the chemical reaction, or we can put it in the chemical reaction. Now you'll notice that when it's in the chemical reaction, it is on the product side because it's an exothermic reaction. When we write it outside of the reaction, we put a negative value here to let us know that it's exothermic, that energy is being released. In the case of the decomposition of ammonia, well, this is an endothermic reaction. That means that energy is going to be added to our reactants. And so it's going to have a positive value associated with it. So we could write it in this form, or we can write it in the form where we have it outside of the reaction completely. And then we just make sure to put a positive value there, or we don't put a sign there. We don't put a negative, positive or a negative. It still means positive. Okay. Questions? Okay, so then I'm gonna go to the next slide, and I want you guys to write the chemical equation, write the two forms of the chemical equation. I'll read it out loud, and then I want you to go through the process. A thermal decomposition of limestone solid calcium carbonate, CaCO3. It's a solid, so yes. To lime, solid, CaO, S, and gaseous carbon dioxide, CO2, G, is an endothermic reaction requiring 178 kilojoules per moles of calcium carbonate decomposed. Write the thermal equation in two forms. So what are my reactants or reactant?
Is it the calcium carbonate 3 solid?
Calcium carbonate.
Uh-huh. And then with the arrow, yeah. And then the COS.
You mean Ca?
I mean CA, yeah, sorry. CO CaO plus CO2.
Okay.
And then on that one, it's endothermic. Wait, I didn't catch that last slide at the end, but is it equals like 178 kilojoules per mole?
So our delta H,
Oh, delta H. Okay, that's it.
yeah, delta H.
Okay.
And so it's, in this case, should be delta HR. You'll see it written both ways depending on the text of the book, but typically it's written after the H, kind of like delta H fuse, you know. And then and that's going to be equal to 178 kilojoules per mole. Okay. So that's one way of writing it. What would be the other way of writing it?
Would it be like the same except at the CO2, would it be the plus 178 kilojoules per
So if it's
or
endothermic, which side of the reaction should it be on?
does it go on the reacting side?
It would go on the reactant side. That's
Yeah.
right. Okay. Questions? Concerns? Cash? Okay. Okay. Now this is a mole problem. Okay. What mass of liquid, let's see. Actually, what we're gonna do is this question I will save for a later date. I'll put it on another slide. This is we haven't talked about a couple of things to figure this out yet. So for right now, we'll just leave it as it is, and then we'll come back to it later on. Okay. So your first exam, the first unit exam, is going to be covering chapters, well, a couple of chapters. It's going to be covering chapters 1, 2, and 3. It's going to cover chapter a little bit of 8. It's going to cover a little bit of 15. And then it's specified under your modules that just tell you exactly the chapters. And a little bit of 10. Okay, this is part of chapter 10, but this part I don't want to go over yet. So there's a little bit more to it. Okay. The practice exam either is posted or will be posted. Your exam is posted. I'm trying to think. You will have, depending on the class that you are, you will have anywhere between, especially since this is also being recorded, from a week to a week and a half. It typically is going to be a Saturday that is going to be due at 11:59 p.m. So it's not going to be, since we're on a Wednesday today, it's not going to be this Saturday, but the next Saturday. So typically I give you anywhere from a week to a week and a half to complete the exam. Are there any questions?
I saw, do we have 2 attempts at the exam?
Let me fix that. You were only supposed to have 1 attempt. There's something that went wrong. Yeah. I need to fix that.
Okay,
It's a single attempt.
okay.
Any other questions? The exam can only be done in 1 sitting, the one on Canvas. I may be moving some of my exams to, or part of the exams to um, active learning, and I think you may be able to do that one in parts. But the overall, you have a certain time limit to get it done. So typically, I give you guys about 2 hours to complete the exam. Normally, I'd say it would take, if you're well prepared, it'll take you about 45 minutes to do it, 45 minutes to an hour. But if you need to sit there and some of us need to think, relax our nerves and stuff like that, and we get worked up. So that's why I give you guys a little bit more time to sit there and work that out. Any other questions?
I have a question about upload. I think we have to like upload some
Yes.
of the like our scratch work or something like that.
Yep. So what you need to do, you're going to upload not your scratch work, you're also going to upload the answers to their short answer questions that you have to work out. So you have to show the work to those. You want to upload those questions.
Okay, and so when we're doing the test, we should do like the multiple choice first and then work on those questions, like the short answer.
Yeah.
Question? Okay.
Yeah. Yes, get the multiple choice knocked out of the way early, and then save the rest of the time for your short answer questions. And then you'll have it has to be uploaded within 30 minutes of that, of you completing your exam. No other questions? Okay, well, it's 10 o'clock. I'm going to let you guys go. And I will see you guys next week on during my cocktail hour next week. on Tuesday. I'll be answering any questions that you guys may have regarding the practice exam. If you haven't already taken the exam. Okay. You guys have a good rest of your week. And I'll see some of you guys, the Harnell students,
Inserted.
in lab on Saturday.